Amphoteric ions. I mentioned these in an earlier video. Essentially, some things can act like an acid or a base, especially if they're part of something that would have been a polyprotic acid. Like as you can see, HCO3 minus here would have been part of H2CO3. They can act acidic or basic. And so what happens if you don't know? All right. So amphoteric ions are ones that can act as acid or a base. Okay. So how do we know which one happens? Does it act like an acid? Does it act like a base? So HCO3 minus, I'm going to look at this. Well, the first thing I'm going to do is write reactions for what happens when it acts like an acid and write a reaction for what happens when it acts like a base. Okay, so I would go HCO3 minus if it was in water and it acted like an acid. Acids donate. So I would get H3O plus and CO3 2 minus. If it acted like a base and put in water, it would grab a hydrogen. So I would end up with OH minus and H2CO3. So which one of these things happens? Okay. First of all, I can look up, you can actually look up the first one, the Ka. This is going to be a Kb, right? Because that first one should look familiar to you. Taking off a hydrogen, the second hydrogen from a polyprotic acid, that would be like Ka2 of H2CO3. Okay, taking off the second hydrogen of H2CO3. Okay, you really need to take a step back and look at these equations. Is this something that I've seen before? Well, I have. That would be Ka2 of H2CO3. That's something I can actually look up, both of those K values. So that is actually 5.6 times 10 to the negative 11. Cool. So then how do I find the Kb of this equation? This doesn't necessarily look familiar. Now you can look at my ions on both sides and be like, okay, well, these guys are conjugates. Do I know what the other one is? It's Ka, right? We do know the Ka of this guy, H2CO3, it's Ka1, right? If it lost 1. The Ka of this is 4.3 times 10 to the negative, I think that's 7, negative 7. Okay, so if you look that up, we can actually find that. So we know that the Kb of its conjugate is going to be Kw divided by Ka. So we're going to do 1 times 10 to the negative 14th over 4.3 times 10 to the negative 7th and get the Kb for this reaction, which is 2.3 times 10 to the negative 8th. Okay, I'm going to kind of box in these numbers. This is for this equation, and this is for this equation. Okay, so why did I do all this? Well, I found the K value for the acid equation. I found the K value for that base equation. And what we're going to do in order to determine, well, does it act like an acid or does it act like a base, is compare that Ka to the Kb to decide. Okay, now what does that tell me? Which one happens? Well, if you remember, a larger Ka means it is more likely to go in the forward direction. So the larger K is the one that occurs more or happens, and that's the one you want to go by. So a larger K is, you can kind of think of it as the winner. That's the one that's going to occur. Larger K is, let's write occurs. Larger K occurs. Okay, so we're going to apply this here in a problem. Okay, so I've got, what is the pH of a 0.050 molar NaHCO3 solution? I had to tell you that HCO3 is amphoteric. Otherwise, you would probably assume it would go one way or the other way. Okay, so I'm going to need this. That's going to be an initial concentration. I need the HCO3 minus. I already decided above that the Kb is, so 2.3 times 10 to the negative 8th. The Kb for this guy is bigger than the Ka, so that means the base reaction is going to happen. So I'm just going to rewrite that base reaction. Makes OH minus plus H2CO3. Okay, I'm going to make my ice table. My initial 0.050, 0, 0, minus x plus x plus x, 0.050 minus x, x, x. So this works just like the other problems we've been looking at. So you just had to decide which one was going to occur first. Since Kb of the base one is bigger, so that was 2.3 times 10 to the negative 8th, That one occurs more, so that's going to be x squared over 0.050 minus x. Yes, you could drop the x. We'll get that x is 3.4 times 10 to the negative fifth. Okay, plug that in here. Oh, sorry. Nope, I was talking about the hydroxide. That's the one that tells us the pH, right? So I'm going to plug that in here. I get POH is 4.47. So that means pH is 9.53. Okay, hang on. Does this make sense? Okay, I got a basic pH. Okay, well, I said Kb was stronger. HCO3 minus should act like a base. So yes, this makes sense. Okay, so what happens if I have conjugates that are both from weak acids and weak bases? So if I had NH4 plus as my positive ion and ClO minus as my negative ion, what happens then? Okay, we're going to do a similar thing to what we just did, and you're going to compare the Ka and the Kb. Whichever one is bigger is the one that occurs. All right, so you're going to write both of these and decide. Okay, for example, like I just gave you this example, if I had NH4 ClO, or let's see, CH3NH3 with F. Okay, either of those things are conjugates of both weak acids and weak bases. So we're going to compare the Ka of BH plus for my example, that would be that. And the Kb of the A minus for my example would be that. And whichever one has the larger K value, it wins, it dominates, that's the one that occurs. And that's the one we're going to use to calculate pH. Okay, so examples 11 and 12 both go with this. If you want to try to do 11 on your own or 12 on your own, I definitely recommend doing 12 on your own, but pause right here and do both. And I will go over both answers when you turn it back on. Okay, so example number 11, I found the Ka of NH4 plus by using, this was the Kb of NH3, something I could look up. I found the Kb of ClO minus by looking up the Ka of HClO. Okay, both things that we did earlier in videos. So the Ka then of NH4 plus is 5.68 times 10 to the negative 10. The Kb of ClO minus is 3.45 times 10 to the negative 7. Well, which one is bigger? 3.45 times 10 to the negative 7. So that's the one that wins. So once I decided that, I wrote the hydrolysis equation on the right side over here for what happens to it, filled in my ice table, used my K value here, and plugged in x squared over 0.08 minus x, solved for x, plugged x back into OH minus, got the POH, and then got the pH, which is 10.22. Okay, so decide if it's acidic or basic, and then do your hydrolysis with your ice to find the pH. Okay, example number 12 just wanted to know, is it acidic, basic, or neutral? So remember, break it into its two ions and check both. K plus is the conjugate of, or it's a group 1 ion, you can think of it that way. You're like, okay, that doesn't do anything. Or you can think of its conjugate is KOH, and that is a strong base, so no, that doesn't do anything. ClO minus is the conjugate of HClO, which is a weak acid, meaning ClO minus will act as a weak base. Part B, CH3NH3Br. Well, Br, that ion, is the conjugate of HBr, so that is not going to affect it because that's a strong acid. So CH3NH3, look at that N, its conjugate acts like a weak base, so this one's going to act like a weak acid. All right, C. I'm going to look at NO3 first. The nitrate ion is the conjugate of nitric acid, HNO3, which is a strong acid, so it's not going to do anything. Fe is a metal ion, but it is not group 1 or group 2, so it does affect the pH. It does make it acidic. We're not calculating those ones. That's in a much later unit. Okay, and LiNO3, if I break it up, I get Li plus is the conjugate of LiOH, or it is a group 1 metal, so it does not affect pH. And again, nitrate NO3 minus is the conjugate of HNO3, which is a strong acid, so it does nothing. So that one is neutral. Good luck.